All right, good morning, guys. Let's get started. So yesterday we were introduced to a new constant, a new number, the number e, right? And it's very important, and it'll pop up a lot in these exponential functions and the logarithms when we get there. So just to remember, e, when these mathematicians were working with that expression, 1 plus 1 over n to the power of n, as they were experimenting with it and they plugged in values for n that got bigger and bigger and bigger and bigger, they noticed that this expression wasn't getting bigger, it was converging and heading towards becoming a fixed number. And that fixed number that it is heading towards becoming is what they named the number e. So e is known as the limit as n goes to infinity of the expression 1 plus 1 over n to the power of n. So the biggest number this expression could ever equal, no matter how big n is approximately 2.718281828. Now, it looks like, wait a minute, does it have a pattern of repeating? Guys, it does not. It's going to go on forever, and there is absolutely no pattern of repeating, okay? So it is an irrational number. All right, the number e is an irrational number or constant that pops up in a lot of different places. It plays a big role in natural growth when something is growing at a rate proportionate to its own size, such as compound interest, like your money. The more money you have, the more interest it can earn, and then the more money you can make. All right, and then populations. Populations grow at a rate that is proportionate to the population. Like they always use rabbits, which I can't stand that, but the more rabbits you have, the more rabbits those rabbits can make. So they grow at this natural growth rate, all right? And it's going to get exponentially big. All right, so that is the number e. So again, the worst thing I want you guys to see it is think it's a variable, because it ain't a variable. It is a number, it is a value that we know. All right, so now we're going to use it, and let's create the graph of the exponential function f of x equals e to the x. So again, don't think of this as a variable raised to a variable. Guys, it's approximately 2.718 raised to a power of x, right? It's a number raised to the power of x. So if the number is approximately 2.718-ish, then it's a base that is bigger than 1. His function should show exponential growth, just like the function f of x equals 2 to the x did, right? But because his base is a little bit bigger than 2, it should start to grow just a little bit faster. All right, let's create his graph. So if I plug in -2, e to the power of -2, guys, bear with me, that's 1 over e squared, right? Let's see if I can fit this in the box. 1 over e squared. And 1 over e squared, just to get a better idea as to what number that is on our calculator, on our graph, it's about 0.135. And again, just to make sure if you guys notice it, everybody should have a calculator. Your calculator has E on it. I have an old one. I don't know if I have my graphing calculator down here. Crap, I don't. But either way, you all have these like log buttons. I don't know if you guys can read this, but there's like the word log right there. All right. So if I hit second and log, I want to get over to the natural log because E is a natural number. And then there is E right there. So I scroll down. All right, I do e, I want to do it to the power of 2, so squared. Oh, God, I'm an idiot with this calculator. I'm so not used to it. Let me do that again. Hold on, wait for the moron to get this right. E, and then squared, and then you hit enter, and then all you have to do is, in order to do 1 over e squared, we all have that reciprocal button. 1 divided by, thank you, Michael. Sometimes I feel like it with this technology stuff. And then you can do where's the reciprocal button on this calculator? I don't know. They all have that 1 over x button, which you could hit, or just do 1 divided by e squared, which I guess I could have done. I always use the reciprocal button. I'm going to stop now because I'm not helping in any way, shape, or form. All right, so 1 over e squared is 0.135. Let's do -1. E to the -1 is 1 over e. So if you do 1 divided by e, that's approximately 0.368, just so we know we're about to put them on the graph. All right, when x is 0, e to the power of 0 is 1. Anything raised to the power of 0 is 1. All right, 1. E to the first power is e, which is approximately 2.718, blah, blah, blah. And then squared. E squared is obviously e squared, which is about 7.389. All right, well, let's do it. Let's graph these points. So we got -2.135, -1.368, so it's slowly getting bigger. 0, 1, all right, now we've made a bigger jump. 1, 2.718, all the way up there. Our jumps are getting bigger. It's starting to get increased faster. And then 2 goes in, and I think it's a smidge off the graph. 7.389 goes in. So there is your exponential growth curve for the graph of e to the x. And again, no matter what number I raise e to, no matter how negative it gets, e to the power of some negative number will never be 0 or equal 0. So it's going to get ridiculously close to becoming 0, but never actually cross over that x-axis and equal it. And it definitely won't become a negative number, right? E to some power will not be a negative number. All right, and there it is. So same thing. It has the HA at the line y equals 0, just like our other exponential functions start out with. It has a domain of all real numbers. There's no x value I couldn't plug in to be the exponent of this function. And his range is from 0 to infinity, just like all other exponential functions in their parent function form before they've been transformed. All right, perfect. So now let's take the graph of e to the x and let's transform it. Let's shift it. Let's stretch it. Let's reflect it. So now they want you to sketch the graph of f of x equals negative e to the x minus 2, right, using transformations. So the first thing I would tell you to do is recognize who the parent function is. You take all these changes away, who's left? Just f of x equals e to the x, right? Okay, well now let's come up with a few ordered pairs that lived on the original graph. The easiest ones to create are when you plug -1, 1, and 1 in. If you want to create more, you go right ahead and create as many ordered pairs as you want that lived on the original graph. All right, and remember the original graph looked like this, showing that exponential growth. So you can picture what changes are going to happen to it. All right, so when I plugged -1 in, that was what? I'm going to leave it in its true form, 1 over e. And then 0 went in, I got 1 out. And then when 1 went in, I got e to the first, which was e. Those were the original points. All right, and he had an original asymptote. Is there anything? Oh.
All right, thank you. I just wanted to make sure I didn't.
Yeah, and guys, last night when I was posting your assignments, I don't know what I've been doing, but I've been sleeping on the job. I have not posted in the past 2 days any filled in notes. I am so sorry. I will make sure that I get all filled in notes posted today after school. I don't know what I've been doing. I just totally forgot 2 days in a row. So I apologize if anybody was like looking for filled in notes. They're not up yet. I'll make sure I get them up with everything today. All right. All right. It started with an HA at y equals 0. It started with a domain of this and a range of 0 to infinity, just in case they ask you to transform any of this information too. All right, well, here we go. Let's recognize the changes. Well, guys, please know that e is being raised to the x minus 2. It's not negative e that's being raised to the x minus 2. This is like a -1 times e to the x minus 2. So you have this -1 out in front of this function that is timesing the y values by -1, which would usually cause some type of vertical stretch, but it's a factor of 1, so they won't be stretched. But you're timesing all the y values by a negative, so it changes all your y values to the opposite sign. So if all of your y values change, it's going to cause this x-axis reflection. All right, so it's going to be negative, oh, I don't want to write it there, -1 times the y's. And then this x minus 2 is a transformation. If I go inside the function and subtract 2 from x, I know that has the opposite effect on my graph, and it actually sends it to the right 2, so I'll add 2 to my x's. All right, so let's do that. So let's make these changes to these original points. All right, so -1 is an x. So take -1 and add 2 to it. Now I get +1, right? It's taking this point and it's bumping it to the right 2 units. All right, take your y value, which is 1 over e, and times it by -1. So now it's going to be -1 over e. And again, just to give you a decimal, that's -0.368. Just so you can visualize it on the graph a little bit better. All right, 0, 1. Where's this point going to go? 0, take it, it's an x, add 2 to it, so now it's sitting at 2. Take 1, the y coordinate, times it by -1, and now you get -1. All right, Next point, 1. Take the x coordinate, add 2 to it. Now it's sitting at 3. E, times it by a -1, and now you have negative e, right? And that's going to be like negative 2.718-ish. Okay, my horizontal asymptote, guys, it used to be at y equals 0. Well, what did I do to the y's? I times them by -1. So if I take 0 and times it by -1, it's still 0. So your HA will still be the line y equals 0. Your domain will still be negative infinity to infinity. It doesn't matter if you shift it right, left, stretch it, whatever, it's still going to be all real numbers. And then my range, it used to be from 0 to infinity, right? Well, if I take my y's and times them by -1, that original y value, when I times it by -1, is still going to be 0. So the range will still be 0 to, oh, that's an x coordinate. Sorry. We'll come back to that one. Let's look at the graph first. I'll show you that when we get to the graph. All right, so let's plot our points. One, it's not an x coordinate. It's still 0 to infinity. We're right. 1, negative 0.368. Now we go 2, -1. And we go 3, negative 2.718. Still got an asymptote at the line y equals 0. So look what you're going to do. You're going to go through these 3 points. You're going to hug that asymptote, right? And then you're going to shoot off with your exponential growth in that direction. So yes, now look at the range. The range is no longer 0 to infinity. Now the range is negative infinity to 0. Because of that x-axis reflection. So again, if you look at the original graph that I drew over here, if you reflect it and shove it to the right too, that's exactly what it should end up looking like. Okay? All right. So just make sure when you do this on the online graphing that the base is E. Sometimes I feel like they did an update on the online and they automatically have the base with the base of that exponential function. Last year, we always had to change the base to the base of the exponential function. So that might just be better for you guys. All right, now the fun part. Let's get rid of the graphing. Let's start solving some exponential equations, right? Get me some equations, get me away from these graphs. Okay. So guys, now we're going to solve exponential equations, and I call it part 1. The reason I call it part 1 is, guys, think about how we solve equations. We solve equations by using inverse operations, right? If the equation was adding, we subtract. If the equation was multiplying, we divide. If the problem was being squared, we square root. We solve equations using inverse operations, right, to undo what was being done. Well, think about it. If we're going to solve an exponential equation where the variable is part of the exponent, we have to use the inverse of an exponential technically, right, to solve it the way we solve equations. And who did I say the inverse to an exponential function was going to be? Who's going to undo an exponential function? A logarithm. We haven't used logs yet. So the reason I call these part 1 is these are exponential functions that you are able to solve without needing the inverse, a logarithm. These ones we can just manipulate the problem a little bit and get away with solving these exponential equations without needing its inverse, the log. All right, so there'll be more exponential equations to come in the next section that you will need a log for. All right, so the reason we're able to solve these exponential equations without a log is based off of this property. If you have base A raised to a power of u, and it equals the same base raised to a power of v this time, then what do we know u and v have to be to each other? If a to this power equals a to that power, then what do u and v have to be? They have to be equal. The only way I could make this true is if the exponents were equal. A squared would only equal a squared. So I'd need my exponents to be equal. Then we know u has to equal v. Okay, and that's exactly what we're going to use to solve these exponential equations. All right, so guys, look at the first example. This is as easy as it's ever going to get. Let's say they asked you to solve this equation for x, right? It says 5 to the power of x, exponential, equals 5 to the -6. Well, if 5 to this power equals 5 to that power, what do those powers have to be to each other? They have to be equal. So all you in reality have to do is set the exponents equal and solve. So I have to have x equal -6. And then lucky for us, there's nothing to solve. That's just the answer. X has to be -6 to make this equation true. If you're going to have the same base raised to a power and they're equal, then those powers better be equal. All right? So that's the whole concept of what we're going to use to solve these problems. So guys, go to the next one. What if 2 to the power of 3x minus 1 equals 32? Well, now we have a little bit of a problem because now we don't have 2 to some power equals 2 to some power. But can we manipulate this and rewrite one of these numbers with the same base as the other? So normally you go to the big number, 32. Can you rewrite 32 as the same base? Can you rewrite 32 as 2 to some power? Yeah, I can. It's 2 to the 5th. So I can rewrite this as 2 to the 3x minus 1 equals 2 to the 5th. So now, if 2 to this power equals 2 to that power, what do these powers have to be to each other? They have to be equal. So all you have to do is set your exponents equal and solve for x. What's it going to take to make 3x minus 1 equal that 5? Set your powers equal and solve. So that's easy. We'll add 1. 3x equals 6, divide by 3, and x has to be a 2 here in order to make this equation true. Does that make sense? Is everybody okay with that? Hopefully that's okay. All right, so again, it's all about manipulation. You need to write both sides of the equal sign as the same base so that you're making this statement of equality where your exponents have to then be equal. All right, look at the next one. 4 to the 2x minus 5 has to equal 1 over 16. Well, again, we're not working with the same base here. So look to rewrite. I automatically see 16 and seeing this base of 4, I'm like, oh, I can totally rewrite 16 as 4 squared, right? But I don't want it in my denominator. So really, 1 over 4 squared, I could rewrite as 4 to the -2 because 4 to the -2 would be 1 over 16. So that's how I'm going to rewrite this one. I'm going to rewrite this one as 4 to the 2x minus 5 has to equal 4 to the -2, right? 4 to the -2 is 1 over 4 squared. It's 1 over 16. So now I have this statement of equality that says 4 to this power has to equal 4 to that power. Well, then what do my powers have to be? They got to be equal. So set your exponents equal and solve. So we're getting around needing a logarithm because we can make the same base. And if we can make the same base, these exponentials won't need a log yet to undo them. All right, so I'll add 5, 2x equals 3, divide by 2, and x is 3/2. Everybody okay? Everybody's good? All right, couple more. Let's say we were asked to solve this exponential equation. Same thing, 5 to the x squared plus 8 equals 125 to the 2x. I right away see the 5. Now, guys, every now and again, you might have to rewrite like both bases. Like if this was a 4, and let's say this was an 8. Well, I can't rewrite a 4 and an 8 as the same base. But a 4 and an 8 can both be written as a base 2. 2 squared, 2 to the 3rd. So sometimes you might have to change both of them into a base they become, but they don't pop up all too often. But just know sometimes you might end up changing both bases to a different base. All right, but here we go. I know 125 is 5 to the 3rd, so I can rewrite that as a base 5. So now I have 5 to the x squared plus 8 equals 5 to the 3rd to another power of 2x, right? And exponent rule, what do we do power to power? We multiply. So now I can get rid of that, and I can say 5 to the x squared plus 8 equals 5 to the 3 times 2x is 6x, and now we're ready to go. If 5 to this power has to equal 5 to that power, then what do the powers have to be? They got to be equal. So set them equal. What's it going to take to make x squared plus 8 equal 6x? All right, well, guys, we have a quadratic equation. So how do we hope to solve a quadratic? We hope to factor it. So let's get everything on one side, set equal to 0, so we can factor it. At worst, we'll use the quadratic formula. I'll minus that 6x over, put everything in the correct order. Let's try to factor this guy. All right, what multiplies to x squared? Xx. What multiplies to 8? That will then add up to negative 6. Looks like we're going with a negative 4 and a negative 2. All right, set your factors equal to 0, and you get x equals 4 or x equals 2. And you end up with 2 answers to your exponential equation here. Everybody okay? All right, we'll do one more. Now we're going to do one with a base e. The good news is everything's already written in the same base. It's all base e, right? I really couldn't take a number and a base e and make them become the same base. So if you're going to do a base e problem, all of your bases will already be base e. It's all just about rewriting, manipulating, and getting it to e to some power equals e to some power. All right, so on the left side, there's really nothing I can do. It's just e to the 2x minus 1. There's no other term on this side that I have to worry about. So let's just leave that as e to the 2x minus 1 equals. Well, guys, over here, we want to make them become one term, one e to some power. There's a couple different things you can do to make that happen. I right away see this e to the 3x, and I want to get them up top. So I'm going to rewrite that as e to the negative 3x to get them out of my denominator. All right, and then you're multiplying it with e to the negative x raised to another power of 4. Power to power, we know to multiply. So that's going to be e to the negative 4x. All right, and now look, on the right side, I'm multiplying the same base. What do we know to do with our exponents when we are multiplying the same base? Like if this was x squared times x to the third, we'd add them. We'd get x to the fifth. Same thing. If this is e to that power times e to that power, when we multiply, let's add our exponents. So this is going to be e to the negative 3x plus negative 4x is negative 7x, right? We're just using our exponent rules. All right, and it still equals the e to the 2x minus 1. And now you have it. You have e to one power equals e to another power. So if that's true, if this really is equal, what do our powers have to be to each other? They have to be equal. So set your exponents equal and solve. So I feel like they're really testing your manipulation skills, your ways to rewrite equivalent statements in math. All right, well, I'm going to minus my 2x's over, and then I'll divide by negative 9. And x has to be 1/9 in order to make this equation true. All right. Everybody okay? Am I making any sense to everybody? Are we okay? Thumbs up? Everybody's good? Okay. All right. So that is everything in section 3 right now. So I did make a homework assignment. I called it 5.3 day 3/4 because we didn't have homework yesterday on day 3. I believe it's about 14 questions. And guys, it's estimated to be quick. So it's a lot of these ones which don't take too much time. Couple graphs with E, and then a lot of these solving ones, which again, to me, I'd do this all day over a graphing problem. All right. Does anybody have any questions for me? Okay, let me take attendance. And then next week we get to start logs. Logs are my favorite. I can't wait.